Hello everyone, I'm Chen Han from Rochester Institute of Technology. Today I want to present our work on ICCV, which is the least square VPT, an efficient and effective approach for visual prompt tuning. So our presentation will include three contents, which are background, our approach, and experimental results. So let's first talk about background. The development of AI should not only consider the performance advance, but also emphasize the sustainable deployment. Despite the pursuit of performance improvement in visual-related tasks, the size of present models has been rapidly increased, resulting in energy-intensive and computational expensive training. Training such large model from scratch will be really challenging, such as limited data and slow convergence at low accuracy. A common paradigm to overcome this challenge is pre-train and fine-tune, which reduce the need for vast amount of training data and speed up processing of various visual tasks. However, the traditional full fine-tuning involves storing and deploying a complete copy of the model parameter for every single task, which remains computationally expensive and not suitable for fast model deployment. To address this issue, various approaches has been deployed, which can be roughly categorized into partial tuning, actual module, and prompt tuning. However, despite achieving promising results, there are two limitations in existing parameter-efficient methods. Firstly, they do not consider the core architecture of the transformer's self-attention mechanism, resulting in a large performance gap with full fine-tuning. Secondly, they usually need to fine-tune a relatively large amount of parameters to achieve reasonable performance and fails to explore the extreme of parameter efficiency. So we consider two fundamental questions. The first one is how can we establish the effectiveness of prompt tuning for large-scale transformer-based visual models? And the second one is how can we explore the extreme of parameter efficiency to reduce the number of tunable parameters? So this is the overview of our E-square VPT framework. Under the pre-train and fine-tune paradigm, only the prompt in the transformer's input and backbone are uploaded during the fine-tuning process, while all other components remain frozen. We further introduce prompting at two levels of granularity, which are token level and segment-wise level, to estimate unfavorable input prompt during rewinding process. So let's first talk about effective prompting. Effective prompting introduces two parts, which are visual prompts and key value prompts. Visual prompts are like traditional prompt tuning method, and the key value prompts include uh, to incorporate into the attention module within each encoder layer. Then we talk about the effective prompting. Since the parameter is now growing by introducing key value prompts, we learn think about having less parameter while preserving the performance gain from these prompts. We then inspired by the lottery tickets hypothesis, showing that there exists a subnetwork that can achieve the same task performance as the original over parameterized network from a given task, without the need for an unnecessary weights. We therefore introduce two-level prompting, which are token-wise prompting and segment-wise prompting. The token-wise prompting identifies and removes the least important visual prompts. After this step, second segment-wise prompting divided each remaining prompt into multiple segments and filter out negative segments. The rebuilding process simply retrain the network with network prompt, enjoying less parameters. Now we show our experimental results on the traditional VIT-based model and swing-based model. You see that all the results will achieve the state-of-the-art method, and we also provide a solid solution for unstable training on different pre-trained objectives. While the other competitors cannot reach satisfying performance when the pre-trained objectives varies, our E-square VPT gets strong performance with the least parameters. And thank you for your interest to our work. We have already published our link and code here for your reference. Thank you.